Okay. So yeah, I wanted a separate video on virtual ground, so that's why I'm starting this again. Uh, so one of you are asking the question: are integrators easier to deal with than differentiators because we have to integrate DE, integrated DE? I'll explain that later. What is the problem with integrators and differentiators when we talk about practical integrators and differentiators later? Yes, integrators are better than differentiators. There is a very simple reason for that. We'll talk about that later when we discuss integrators and differentiators. So right now, I want to discuss the idea of virtual ground. Okay, virtual ground is a very interesting concept that you will encounter in op-amps. So right now, since you have gone through different levels of courses in electrical engineering, when I was a student, when I was a teenager in high school, you must have studied about the concept called ground, or you must have heard this concept called ground in household connections. So our logic would always be that's a point which can take away all the electrons. Okay, it can quickly take away all the electrons, drain all the electrons. So my first thought when I heard the ground as a teenager was it's a point which can sink infinite current. Okay, and it will always maintain this same voltage. Okay, same potential. It's a point that can sink infinite current. But then once we start with basic circuit theory courses, you are used to another definition of ground, where ground is used as a reference node in the circuit with respect to which you measure every other node voltage in the circuit. Okay, you measure every other node voltage in the circuit using that reference voltage, using that as a reference point. So for example, let's take this circuit here. It's a 1 volt connected through to 3 resistors in series. If I define this node as ground, then this node is at 1 volt. Okay, remember voltages are usually defined with respect to a ground because potential, electrostatic potential, is generally between 2 points. You define it in between 2 points in space. So therefore, I can't say that I can't directly ask you what is the node voltage for a given node. You're always measuring that voltage with respect to some other node, some reference node. And that reference node is what we call ground. So there is no practical significance to it. It just helps in analyzing circuits. It's just a way of seeing what's happening in a circuit. So a ground is just a reference point. It can be arbitrary. You can define any node as a ground. If you define this node as 0, then this node is at 1 volt. So remember, if you apply, assume all the resistors are of 1 ohm. All the 3 resistors are of 1 ohm. And what is the total current flowing in the circuit? It's a 1 volt circuit. It's 1/3 of an amp, right? 1/3 of an ampere is the current flowing through that. So what is the voltage drop across each resistor? The current is 1/3. The resistance value is 1 ohm. So each resistor has a voltage drop of 1/3 of a volt. Each resistor has a drop of 1/3 of a volt. So if this node voltage is 1, if you drop 1/3 across the resistor, then this node voltage will be 1 minus 1/3. That will be 2/3. Now the current direction is here. So this node voltage will be 2/3 minus 1/3, which will be 1/3. So this node voltage will be 1/3 minus 1/3. It is 0. So now if I define this node voltage as 0, I was able to define the node voltages for other 3 terminals. It's 1, 2/3, and 1/3. Now I will define this node as 0 volts. I'll choose this as my ground, which is 0, as my reference node, whose voltage I'm defining it as 0. Then this node voltage will be -1, right? This is because it's a 1 volt DC source. This terminal should be at a potential of 1 volt higher than the negative terminal. And if I set the positive terminal is at 0, then the negative terminal will be at -1. Now I'll start from here. If this is 0, and I'm dropping again, the current flows in the loop, the current direction, everything remains the same. only your analysis will change. Okay. So if you're dropping 1/3 here, 0 minus 1/3 will be minus 1/3. That's the node voltage at this point. You subtract another 1/3 because the resistor is dropping another 1/3. You get minus 2/3 here. You subtract another 1/3 from minus 2/3, you get minus 1. So now if I see it's the same circuit, everything, the resistors are carrying the same current, the potential drop across the resistors are all the same. But I just changed the ground to a different point. I just called this node as 0 and see what happened to the node voltages. All the node voltages changed. Okay. So the node voltages are very different because your reference point is very different in both the circuits. So this ground is what you are used to when you learned a basic circuit theory course, right? When analyzing circuits is very useful. In fact, all your simulators, your circuit simulators like LT-Spice or Cadence, Spectre, and other simulators, they do the same. They define one node as ground. You usually have a symbol called ground, and it's going to take whichever node you connect to that, it will treat that as ground and do the circuit analysis. Okay, this is what it's internally doing. It's defining one node and defining potentials for every other node. So this is something that you are aware of. A ground is a reference point for analyzing the circuit. With respect to, once you define that reference, then you can define every other node voltage in the circuit. The next ground that you must have encountered is the AC ground. Okay, this is something that you must have encountered when you started studying amplifiers, basic amplifiers in your introductory courses, right? How to analyze single stage amplifiers and all that. Where normally you AC couple your input signal, which is input signal happens to be a sinusoid of some frequency. And the circuit is supposed to produce an amplified version of the input signal. Now here, I've connected the source terminal. See, this is a MOS-based circuit. Since you have already done a basic MOSFET, a course on microelectronic circuits, can you tell me what is the DC voltage at this node? What is the gate voltage, DC gate? Okay, what is the DC voltage at the gate terminal? Here I have two DC voltage. One is VB, other one is VDD. What is the DC voltage at the gate terminal? No, DC voltage. There is no frequency dependence here. Forget about frequency dependence. DC. You can treat capacitor as an open circuit. If you treat capacitor as an open circuit, what do you get? What is the DC voltage at the gate terminal? The input gate current is 0, right? You can assume ignore gate leakages. The input gate current is 0. If the input gate current is 0, then what is the gate DC voltage here? See, this node is at VDD. This is a common ground. What is this node voltage here? The gate current is 0. Therefore, the current through the resistance RB is also 0. Then the voltage drop across RB is also 0 volts. If that is 0, VDD, right? That's it. It's just VDD itself. So your gate voltage is just VDD. And your source voltage is at VB, capital VB. Okay? But there is a difference here. In case of gate, there is a resistor that's connecting to VDD. Okay, here you have directly connected a supply voltage to the source terminal. Now, what is the definition of a voltage source? An ideal voltage source is one. Let's assume one node. I can probably draw it this way. An ideal voltage source is one. It will always maintain the voltage across its two terminals to be constant. This is an independent voltage source. No matter what the current, you can inject a huge current into this node. The voltage source will absorb it. Or you can remove a huge current from that node. The voltage current will provide the current. But the node voltage between these two terminals, the voltage across the independent source will always remain constant. Okay, so that's why it's called an independent voltage source. If I draw the voltage versus current characteristics of an independent voltage source, it will look like this. Whatever be the current, even if you push infinite, plus infinity or minus infinity of current, the voltage will always stay, it will always stay put at VB volts. That's the property of an ideal voltage source. Its voltage will not change at all. So even when you apply a sinusoidal voltage signal, when you apply a sinusoid here, you can treat this capacitor as a short circuit. You can treat it like a short circuit for the AC frequencies of interest. So your gate will be seeing a sinusoidal variation. What will be the voltage? What will be the voltage at the source? Will there be any sinusoidal variations at the source? Will there be any variations at the source terminal? I have forcibly connected it to a DC voltage source. You will see no variation at all, right? Therefore, we call this as AC ground. We call it a ground because it's not changing at all. The node voltage is not changing, even if you inject AC current. Remember, there is an AC current flowing in the circuit. The gate current in this, the drain to source current in the MOSFET, this drain to source current is because of this AC signal. That's sinusoidally varying. However, this voltage source is an ideal voltage source. It can carry AC, DC, it can carry huge amounts of current, but it will always maintain its voltage constant. Therefore, this node voltage will not change at all for AC. As far as AC is concerned, it will not have any change. So this node will be AC ground. Is there any other AC ground in the circuit? In the circuit, is there any other AC ground?
VDD.
Yes. VDD itself is AC ground, right? This is also constant. It will always remain the same. So this is again AC ground. Okay. So second ground that you would have encountered is what we call the AC ground. Okay. Which you would have used for small signal analysis. When you have an amplifier, you remove all the capacitors, short circuit the capacitors, and open circuit current sources and all that. The second ground that you would have encountered is what we call the AC ground. Okay, this is normally encountered when you're analyzing amplifier circuits. Okay, so I've drawn here a small signal equivalent or the AC equivalent circuit for this amplifier. Okay, so this is the two grounds that we have encountered so far. But since you have done microelectronic circuits where you have studied differential amplifiers, we encountered a third ground called the differential ground. Not just AC ground. There is a small difference between AC ground and differential ground. We'll see what it is now. So let's say I take two resistors of similar values, R and R. And I connect two voltages, VI and minus VI. Then what is the node voltage at this center?
0.
0, right? It's the average of the two voltages, which is 0. But if I connect VI and VI, both are AC signals. Okay, both are AC. What will be the voltage at the center? VI and
VI only.
VI itself, right? The average of VI, two VIs, VI plus VI by 2 is VI itself. So you will get the same voltage here. So which means I'm applying AC signals. Remember, these two are AC signals. These two are sinusoids, small signal sinusoids. This node is also a sinusoid, same sinusoid of similar frequency, of same frequency. So here, this is not AC ground. Even though I'm applying AC signals here, this is not going to ground. This node voltage is changing. But if you see here, if I apply differential signals, if I apply plus VI and minus VI, only when you apply differential signals, this node goes to ground. This node is at 0 volts. It doesn't change at all. So this third ground is what you call the differential ground. Okay. And this you will encounter in differential amplifiers. So look at this very simple differential pair where I've used a current source biasing. So I've applied plus Vi by 2 minus Vi by 2. Okay. I've applied plus and minus Vi by 2. So can you just tell me if VDD is AC ground uh, or is it DC ground, or I mean, is it AC ground or differential ground? VDD.
So it's both AC and differential.
It is both AC and DC, right? For AC, it is constant anyways because it's a DC voltage source. So its voltage cannot change at all. At the same time, you have two resistors here. See, these two nodes are differential because it's a differential amplifier. These two nodes are differential. Since these two nodes are differential, this has to be a differential ground as well. So this node happens to be both a differential and an AC ground. So to make matters simpler, let me just connect a resistor here. Resistor R. What about this node? Is it an AC ground or is it a differential ground or what is it?
So the lower node.
Yes. This node. Here's this one here.
It is AC ground, but not DC ground.
No. See, remember, we only discussed two grounds here. It is not DC ground, obviously, because the DC voltage is finite here. Okay, that's true. But what about AC?
In
Is it
differential
really AC
amplifier,
ground?
it has to be AC grounded.
Now, for example, let's assume I apply two sinusoidal signals which are of same polarity, Vi by 2 and Vi by 2. Do you think will this go to ground? If you apply a common mode signal? No, right? It won't go to ground because you can treat it like, if you ignore channel length modulation, you can treat it like two source followers. Okay. So this is not an AC ground. It's not AC ground. AC ground means whatever AC, when the moment I apply AC signals to the circuit, whether it's differential or common mode, this node should go to ground. It doesn't. Only when you apply this to be a differential input. If this is plus Vi by 2 and minus Vi by 2, this node will come to ground. Because it's a purely symmetric circuit. If this amplifier is trying to drive this node by some amount, this will drive it by the same amount in a negative polarity with a negative polarity. So this node voltage will come to ground. Okay. So this ground is a differential ground. This node here is a differential ground. A differential AC ground. I should use the word differential AC. Okay. It's not common mode wise. It's not zero. If I say common mode AC, it's not a common mode AC ground. Okay. So here AC I'm using as a very generic term to indicate both differential and common mode. So when I said it's not AC ground, what do I mean? It's that it's not ground for common mode signals. Okay. It's ground only when you apply a differential AC signals. Okay. So now let's analyze the second circuit here. So in this circuit, can you tell me how many AC grounds are present? AC ground. So when I say AC ground, I'm referring to it has to be both common mode and differential grounds. Okay. It can't be just how many pure AC grounds are there in the circuit. Ignore channel length modulation. Assume the circuit is perfectly symmetric. If you assume the circuit to be perfectly symmetric,
Sir, if there's a differential input, then
yeah.
there's 4.
If there is a differential input, how many nodes are differential grounds? How many differential grounds are there?
No, AC grounds are 4, differential are 2.
Yes, differential grounds are 2, right? One is
Yes.
that this node is a differential ground, and this is also a differential ground. Because it's a purely differential amplifier, this node will be, these two nodes will also be differential. Because these two nodes are differential, the node at the center will be at AC ground. Similarly, this
Yes.
node will also be at AC ground.
Oh,
Okay, this node will also be at differential ground. So there are
not AC
two,
ground.
not AC ground. So there are two differential grounds. There are two differential AC grounds in this circuit. Okay. Now, AC ground, VDD will be an AC ground because that's a voltage source itself, right? So it will be an AC ground. It will be AC ground even if you apply common mode inputs, or if you apply differential inputs, it doesn't matter. This node will be at ground. But for these two nodes here, this node and this node to be at ground, you have to apply differential signals. Only when you apply purely differential signals, these two nodes will come to ground. So therefore, those two are differential AC grounds. Okay. For if you apply common mode signals, they will not be at ground. They will not be at AC. So there is only one AC ground in the circuit, not four. There is only one pure AC ground. When I say AC ground, it's ground for differential inputs. It's ground for common mode inputs as well. Okay. So that's something to keep in mind. So this circuit has VDD one AC ground. When I'm using the word AC, I'm referring to both. When I say AC, it has to be ground for both common mode and differential inputs. That happens only for VDD. This node here will be only a differential AC ground. It's not ground for common mode inputs. Okay. So if you understood this, I'll stop at this point. Okay. We'll discuss the concept of virtual ground in the next lecture because I just introduced you to different grounds here.